So I wanted to add another topic before we go off to winter break here. Another thing related to rotation, and this is a something we'll use quite a bit, which is called rolling without slipping. So imagine, if you will, that we have a pool table, felt-covered pool table, and we have a cue ball, and somebody strikes this cue ball with a cue stick. And the cue ball begins by moving in a sliding fashion. That is to say that the bottom edge is skidding across the felt, and all the parts of the cue ball are moving at the same velocity to the right. Now, this condition will not exist forever because there is some frictional force at the bottom edge of the cue ball. I love the fact that I've drawn my pool table with some sort of rise and fall, but you'll have to imagine something a little straighter. So as it's sliding, there is a frictional force this way on the cue ball. And that frictional force is going to start the bottom edge slowing down. And the top edge will remain going the same speed. So we're going to begin to spin. And that's because there's a torque here, okay? There's a torque, which is R cross F, R being the radius of the ball. And that torque is going to give rise to an angular acceleration, and that angular acceleration is going to give rise to an angular velocity. But that process does also not go on forever. You see, at some point, the ball will begin to be moving in a rotational fashion at such a speed that the bottom edge is not moving relative to the felt. In other words, the top edge will be moving at some velocity, actually twice the velocity of the center of mass, and the bottom edge will have a velocity of 0. And at this point, the spinning is such that the bottom edge is not moving relative to the felt, so there will not be any more friction. This point is instantaneously at rest with regard to the surface, and so there is no friction. There's no attempt, so there's no more torque, and so there's no more angular acceleration. This will have lost angular speed and lost linear speed and picked up angular speed such that omega times r equals v. This is a relationship I gave you last lecture about how the angular and linear speeds are related, but that's the relationship between the angular velocity of the ball that is rolling without slipping. So I should probably put here that this is a picture of rolling without slipping. Okay, and so notice on the rolling without slipping ball that the bottom edge is instantaneously at rest. The middle, the center of mass of the ball is moving with a velocity v, and the top edge, because it's going forward with as much differential velocity than the bottom edge is going backwards, is moving with a velocity 2v. That's kind of interesting. And in fact, you may have seen log rolling contests where someone will actually stand on top of a log on the ground, and so now I need to draw their shoe. And they will actually walk backwards as if they were going to walk backwards, which moves the front top edge of the log forwards, and the entire log moves forwards with a speed of half of the velocity that the person is moving. This relationship is valid. There's another thing that's really interesting about this rolling without slipping phenomenon. Well, two things. One is, if you don't smack the cue ball with a cue stick, if this is just gently started, then it will begin by rolling without slipping. Friction will hold this point in place while you start the thing rolling. So when a car takes off, as long as you don't punch the gas pedal, you begin by rolling without slipping. Now, those people who punch the gas pedal or rev up the engine and then drop the clutch, if you have a manual transmission, you can get this spot here to break free and have friction and slide against the ground, and that's really kind of murder on your tires. The one more thing I wanted to say that's interesting about this is when one of these balls rolls along without slipping, and I know I'm not touching the surface here, but a very interesting thing happens. We're going to keep track of one point. We're going to start here at the bottom. As this thing rolls, that point begins by moving straight up, then arcs over until that point becomes the top, and then it arcs over again until that point becomes the bottom. And this shape is called a cycloid. It's not a cosine curve, even though it kind of looks like one. And of course, how much distance do you travel? Well, when the point goes from being at the bottom to being at the bottom again, well, you would travel the circumference of the wheel to do that. So the point goes from the bottom to the top and then back to the bottom. So if you roll over a stone and it gets stuck in your tire, the stone's motion will first be straight up and then will have some horizontal motion. It'll be moving in its maximum horizontal way when it's going across the top of your wheel, and then it will move back down until it is instantaneously at rest again with the ground. So that's the kind of shape it has. So this is all rolling without slipping. It is a fun thing to do, and only when something is rolling without slipping can you establish this relationship that you might use to get rid of the angular variables in a kinetic energy expression, as we discussed last time. Okay, that will do it before the winter break. Please have a good one.